I am a professor at Virginia Tech of Aerospace and Ocean Engineering. I've been at Virginia Tech for 16 years, but I've been studying the three-body problem for over 25 years. I got started when I was an undergrad as an intern at JPL, did some work with the Genesis sample return mission, if anyone's familiar with that. It went to the Sun-Earth Lagrange points, brought back some material. And since then, I've done some other things looking at multi-body dynamics and mission concepts related to that, like a multi-moon orbiter for the moons of Jupiter, and also the use of cislunar space, like a gateway station at the Lunar L1. Because from there, that's basically the doorway to the rest of the solar system. So this is an example trajectory designed in the restricted three-body problem. It goes from a georadius orbit out to an orbit around the moon. I'm showing it in the inertial frame that we're used to seeing things, and then the rotating frame that I'll be introducing as sort of the main frame if you want to look at the three-body problem. And you'll see right here at the end, there's this little pass by one of the Lagrange points, and then this gets onto a stable lunar orbit with a periloon of about 14,000 kilometers. And I'm going to revisit this several times because it has a bunch of different ingredients. This multi-pointed star shape represents a mean motion resonance, but as seen in a rotating frame. And then these libration-point dynamics get involved, even though we're not necessarily getting onto a halo orbit or a Lyapunov orbit or other orbits that maybe you have or have not heard about. Here's another way to get to the moon that actually uses the sun's perturbation. So using a solar perturbation, just from one delta V, leaving an Earth orbit, this gets caught into a ballistic capture, temporary capture around the moon. With a small delta V, this could be a permanent capture, but this is very non-intuitive, going out basically 4 times the distance of the moon. So this just shows that 4-body dynamics are at work, but the basic ingredients are 3-body dynamics. We can actually understand this as 2 patched 3-body systems. So there's a big jump going from the 2-body to the 3-body. I'm not sure if there's an equivalent jump going into the 4-body dynamics. You can kind of break it down into 3-body dynamics. So I'm going to be giving you an idea of how the 3-body dynamics works. So we'll be talking about the restricted 3-body problem. I'll give the equations of motion. There's also a very important integral of motion, a constant of motion, Jacobi integral or Jacobi constant. It's related to something called the Tisserand relation. I'll mainly be talking about Lagrange equilibrium points and the motion around them, because that's definitely unique to the 3-body dynamics. I'll talk about tadpole and horseshoe orbits, and then Lyapunov and halo orbits, which you could think of as maybe kidney beans and potato chips. Sounds yum, huh? Then invariant manifolds and periodic orbits. This is when we'll do a little MATLAB script. Finally, at the end, I'll say a little bit about mean motion resonances and the chaos related to them and navigating around mean motion resonances from the 3-body perspective, and also how cislunar space is basically connected to heliocentric space. So the circular restricted 3-body problem is a special case of the 3-body. So the 3-body problem is where you have 3 massive bodies and they all influence one another. When we say circular restricted, we mean that there are 2 massive bodies, M1 and M2. They're circling their barycenter. So they're on a circular orbit. They solve the 2-body problem. In this case, we're assuming a circular orbit. And then we've got a test particle P, so something that's much less massive, does not influence the motion of M1 and M2. So spacecraft and asteroid. And we view this, we could view this in terms of an inertial frame. So this would be the moon's orbital plane. But usually we look at this in terms of a rotating frame. So a frame that's along the Earth-Moon line, so this little x direction. And that rotates with a frequency omega, which is 2 pi over the period of the moon's sidereal motion, which is 27.3 days. And then we have a whole coordinate system that rotates, keeping the Earth and moon fixed. So in that frame, in this rotating frame, the equations of motion are simplified because we'll have a right-hand side of the equations that doesn't explicitly depend on time or equivalently the phase of the moon. Because the Earth and Moon in this frame are fixed. We do some rescaling as well, so this is common for understanding the three-body problem. There's a common framework, which is that the distances are scaled by the semi-major axis of the two massive bodies. So in this case, the Earth-Moon semi-major axis, 380,000 kilometers. Time is scaled by the rotational period of the Moon divided by 2 pi. When you do that, the gravitational constant is, in these units, is equal to just 1. So it basically falls out of your equations. And the only parameter that's important to the qualitative dynamics of this test particle P is something called the mass parameter. It's the mass of the smaller massive body to the sum of the two. So this would be the Moon over Earth plus Moon, which is about 0.01215. And this is actually very large by solar system standards. The Sun-Jupiter, which we've understood a lot of things about the three-body problem by understanding the Sun-Jupiter system. There, it's about 1 over 1,000. This is an order of magnitude higher. And actually, when you go to higher mass ratios, new phenomena can happen. So not only is it this Kirkwood gap analogy for the cislunar space significant, it could be very different. There could be new phenomena that we just can't even pick right now. So in this frame, and with these rescalings, the Moon is located at 1 minus mu, and the Earth is located at minus mu on the x-axis. The equations of motion for the spacecraft are the motion in an effective potential, and I give the effective potential here, what it looks like, plus a Coriolis force. Remember, we're in a rotating frame. So this effective potential includes gravity due to both the Earth and the Moon. This is just a constant that's included for convention. This term gives the centrifugal force, but then there's a Coriolis force, which will show up. This is what the effective potential looks like, and you'll see there are these significant points. We'll say something about that. But just again, that example that I showed before, viewing things in an inertial frame compared to viewing things in a lunar rotating frame. This is the preferred frame for doing three-body problem computations and analysis. This is just showing it, again, one-day tick marks. So the equations of motion, when we non-dimensionalize them, we get this set of second-order ODEs. So this is for how the particle P is moving in terms of x, y, and z. So Cartesian coordinates in the rotated frame. We put this in first-order form, and we have 6 first-order ODEs. And there is a constant of motion. There's only one. In the two-body problem, there are 5 independent constants of motion. Here, there's one. One that we can write analytically. And it's this E. So I might refer to this as the three-body energy. And it's 1/2 the velocity squared with respect to the rotating frame, plus this effective potential. Now, I'll be using the three-body energy most of the time, but there's another term that gets used, the Jacobi constant. So this constant of motion is sometimes written in terms of the Jacobi constant. The relationship is E equals -1/2 of the Jacobi constant, C. Now, like I said, this looks like the usual 1/2 velocity squared plus potential, but this is the squared velocity with respect to the rotating. Now, Tisserand noticed in the 1800s that he could write the Jacobi constant formula as approximately equal to negative the two-body energy plus the z component of the angular momentum. And when you write that out in terms of the geocentric orbital elements, you get that 1/2 Cj is 1/2a. And this is all in non-dimensional coordinates. So here, a equals 1 would be a radius or a semi-major axis equal to that of the Moon. And this inclination is with respect to the Moon's orbital plane. So this is the negative two-body energy plus z component of angular momentum. What this can be used for is for understanding how what happens before and after a close encounter with the moon. So this is just showing some schematic of a trajectory that has a close approach to the moon. If we know what the orbital elements are before a close encounter, that should equal what the orbital elements are after the close encounter, even though these could be dramatically different. So just to show that, again, these geocentric orbits seem to jump along Tisserand curves. I say jump because the timescale of a close encounter is just much shorter than the geocentric orbit. So if we look at an AE plot, again, this is in the non-dimensional coordinates. I'm showing curves of constant Tisserand parameter, or Jacobian constant, when we have an inclination of 0. So let's say we have the same situation. This point represents our A and E before the close encounter. The close encounter is very quick, and then we're on another orbit, but they're on the same curve of Tisserand parameter. Now, the Tisserand parameter is approximate. There should be some terms of order mu, so that would be the small parameter here. This also assumes that the moon is on a circular orbit. Because it's not, this how conserved this is will change somewhat. And that comes from energy. Another thing we get from this three-body energy is that the space is divided into different realms of motion. So what I'm showing here is for a particular value of that three-body energy, and just looking at the moon's orbital plane, the white region is where the spacecraft can be. The gray is not. It's just energetically forbidden. And this is in the rotating frame. You wouldn't have anything analogous in the inertial frame, so you have to do this in the rotating frame. The boundary of this energetically forbidden zone is called a zero velocity curve, because the velocity goes to 0 with respect to the rotating frame at those locations. In fact, trajectories seem to sort of bounce off of it as if it is billiards. So this is a case where there's a realm around the Earth, and I'm talking not just projected onto the position space, but phase space as well. So there's a realm around the Earth. Think of that as mostly geocentric orbits, the realm around the moon, and then there's a realm exterior, which are also geocentric orbits. And as the energy changes, these different regions get connected. So let me show this video. This is by a former master's student, Matt Werner, who is at the Aerospace Corporation in Austin. We just started, I think, 2 months ago. Anyway, this is showing the effective potential surface, and we're increasing the energy, showing what these zero velocity curves do as we pass through different points. So at the lowest value, all the regions are disconnected, and then you see as energy increases, their connections or necks start opening up, first at this red dot, and then at the green dot, and the blue dot over here. So this is L1, L2, and L3. And they're ordered that way because of energy. And then we've got L4 and L5. So there's different qualitative cases. The first one, case 1, is when the energy, so the three-body energy of the particle is below that of L1. So the particle's either completely outside, around the moon, or around the Earth. So the vast majority of things that are studied, this conference are in case 1. Case 2 is where the bottleneck opens up at L1. So we're at an energy that's in between that of L1 and L2. Case 3 is where the energy is between that of L2 and L3. Case 4 is where it's greater than L3 but less than L4. And then beyond, and case 5 is where you have energy greater than L4 or L5. There are no more energetically forbidden parts of the position space, at least in the rotating frame. That was showing a cross-section through the moon's orbital plane, but these are surfaces in 3D as well. So here's the zero-velocity surface in 3D. This is another view showing some zero-velocity surfaces and the cross-section through it with a trajectory. This is a trajectory around the Earth, and then a trajectory around the moon, and they would be connected through, kind of passing through some neck or bottleneck region around L1. So in this circular problem, trajectories cannot pass through these zero-velocity surfaces when they exist. So we cases 1 through 4. So those neck regions that we're opening up are related to what are called the collinear equilibria. That's L1, L2, and L3. Another thing to note is that there's something called the Hill sphere, and this is roughly the sphere of influence of the moon. And it's about 60,000 kilometers, and basically is a sphere with the same radius as L1 and L2, which are about equal distant from the moon. Notice that these points are critical points of this potential energy surface. So I'm going to say some about the location of the Lagrange points. First, L4 and L5. So these are called either the triangular or equilateral points. These are locations 60 degrees ahead of the moon and behind the moon in its orbit. And if you're there, it's equidistant between a spacecraft there is equidistant from the moon and Earth. They're also known to be stable for the value of the mass parameter that exists in the Earth-Moon system. We can look at the linearized motion around the L4 and L5 just to get an idea of what types of trajectories can happen. So this is the full nonlinear ODEs. But if we translate our coordinates so that the Lagrange point is now the origin, and then we keep only linear terms from those from the derivatives of the effective potential, we get something that looks like this. This could be written in matrix form, and we can calculate eigenvalues from it. So from the constants that we get for L4 and L5, we get 6 eigenvalues, and they're in the form of 3 imaginary pairs. So the first one, this is omega 1. It's approximately equal to 1, and this represents short period planar motion, so with a period of 2 pi. 2 pi in these non-dimensional coordinates means 1 month. So you already know. Omega 2 is around 0.3, so this represents longer period planar oscillations of a period of about 3 months. And then we have vertical oscillations. So if we look at the motion, at least in the lunar plane, it's epicyclic. What we have is quasi-periodic motion. Quasi-periodic just means there isn't one frequency, there's more than one frequency. In this case, we're showing 2 frequencies. So there's a short period motion with a period of about 1 month. And that is represented by the small ellipse, so the black dot moving around this white guiding center. And that superimposed on this, we have a longer period motion with a period of about 3 months. And that's the large ellipse. The small ellipse has a ratio of 2 to 1. The larger ellipse has a ratio of about 5 to 1. And if we start with some initial condition and just follow it, that's what's shown as this thin line. You can see the epicyclic motion. Quasi-periodic. Now, L4 and L5, because they're stable, it could mean that objects could collect there. So I'm showing the Trojan asteroid population in the Sun-Jupiter system, which are, it's L4 and L5. It's possible things could collect in the Earth-Moon system as well. If we look at sort of larger amplitude, so beyond the linear approximation, if you just started with some initial condition and followed it forward, what you get is something that's kind of non-linear, this sort of tadpole shape. So these, because the shape represents a tadpole, they're called tadpole orbits. Slightly different initial conditions make it so that this tadpole actually its tail keeps on going, and you get what look like kind of 2 tadpoles. But because it resembles a horseshoe, we call them horseshoe orbits. This shows a lot of these epicycles. We take some different initial conditions and it looks more smooth, the horseshoe. And it's instructive, I think, to see what this looks like in an inertial frame and a rotating frame. So these horseshoe orbits, they have this strange periodic encounter with the moon where they get pushed from an orbit that's completely outside the moon's orbit to one that's completely inside. And I think you get more insight looking at what's happening in the rotating frame. Going around this C shape, the horseshoe shape, with these close encounters. And this seems to include L3. This is another trajectory. This isn't in the Earth-Moon system. This is in the Sun-Jupiter system. But this is a comet during most of the 20th century. So from 1910 to 1980. Comet Oterma, it started out outside the orbit of Jupiter, had a close encounter where it is now inside the orbit of Jupiter, and then it meets up again, and it's on the outside. So this changed its orbital elements dramatically. Of course, it didn't do any maneuver, it just had a close encounter. So if you looked at the semi-major axis, divided by the semi-major axis of Jupiter, see it starts here, and then something crazy happens, that's a close encounter. It's down here, and then you have other things. So it may not make much sense to look at this in terms of heliocentric orbital elements. If we look in the rotating frame, things may make some more sense. This is the trajectory in the rotating frame, and you see Oterma is passing by these Lagrange points L1 and L2, and it seems to be phased just so that it comes in, and then it does this sort of three-pointed shape, and then comes right back. This is actually an example of what's called a resonance transition. And the comet really did do this. You see that we're in this case 3 regime. I'm showing the projected onto the Jupiter's orbital plane, the zero velocity curves. So the only way to go from the outside to the inside had to be through a close encounter, which is what happened. There's actually other objects that have been captured for longer, and in fact, Shoemaker Navy 9 that slammed into Jupiter seem to be on in a similar energy regime. So this isn't a horseshoe orbit, even though it might kind of grossly resemble it. And you can see that L1 and L2 are definitely involved. So I'm going to say some things about that. The location of these collinear points is not as simple as the triangular points. It varies by the value of mu. And of course, we've got the Earth-Moon view. This is actually shown for the Earth isn't to scale here, but this is showing where they are to scale with respect to the Moon's orbit. And these points, L1, L2, and L3, are all unstable. If we were to, well, one way to find them is if you were to look at that effective potential just along the x-axis, you get this plot, and the local maxima tell you where L1 and L2 are, and L3. We mostly focus on L1 and L2. And if you look at the distance from the Moon to each point, so gamma 1 for L1 and gamma 2 for L2, these distances are given by a solution to a fifth-order polynomial, where the upper curve is for L1, the lower curve is for L2. And this is all in non-dimensional distance units. So you notice we've got some terms here. There's some approximate solutions that are based on the Hill radius. The Hill radius, I mentioned that earlier as being the sphere of influence for the Moon. And in units, it's about 60,000 kilometers. But in the non-dimensional units, it's about 0.1594. So the gamma 1 is 1 Hill radius minus 1/3 Hill radius squared. Gamma 2 is 1 plus 1/3 1. So L2 is going to be a little bit further away than L1. So let's look at what the motion looks like here, L1 and L2. We'll use the same kind of procedure of linearizing. So again, these are the full nonlinear ODEs. You can translate coordinates, so the Lagrange point is at the origin, and then keep only linear terms. And here, A, B, and C are all positive real constants. The eigenvalues here are different from L4 and L5. We have 6 eigenvalues, and you'll notice there's a real pair, so plus or minus lambda. Because this is real, and we've got something in the right half plane and something in the left half plane, this means that this relates to both stable and unstable motion, or approaching and departing dynamics from the equilibrium point. And then we have an imaginary pair that's related to planar oscillations, and another imaginary pair related to vertical oscillations. And it's based on that, we can actually work out that there are 4 different types of trajectories near L1 or L2. So I'm just showing schematically what they are here. But we've got bound orbits. So these are orbits that are either periodic or quasi-periodic. So for example, halo orbits would be here, or Lyapunov orbits. Then we've got trajectories I'm showing in green that are asymptotic to those bound orbits. So these are asymptotically approaching or departing those bound orbits. And then there are the transit orbits. They go from one side of one of these neck regions to the other. There's also non-transit. So these approach a neck region and then they just bounce back. And one can work this out in detail. I'm not going to show it here. We could also look at the solutions to the linearized equation, the ones that are bound. So these are bounded solutions. So they only include, we'll see the frequencies omega p and omega b, so the planar and the vertical oscillations, and some amplitudes that we can choose, ax and az. So this is, again, quasi-periodic motion for the bound orbits. And the amplitudes ax and az represent the in-plane and out-of-plane motion. So they characterize the size of the orbit. So I'm showing 3 different projections. This would be the projection onto the moon's orbital plane. So we've got ax is the half width in x, and then ay is just given by kappa ax, where kappa is given by some constants. Az is then independently chosen. So this is now the xz projection. So from these 3 different projections, maybe it's not clear what these look like, but this is what trajectories look like. So these are the linearized solutions, linearized dynamics near L1 or L2. I think it looks like winding around a muffler. So car mufflers, right? If the frequencies are equal, then we have periodic motion. But this only happens when the amplitudes are large enough that nonlinear contributions become significant. And there's some theory behind getting some analytical approximations to it. I'm just going to show you the results. So these are the halo orbits. So they've got, this is the x, y projection. You can sort of see they're sort of bent. And they're called halo orbits because seen from the Earth, they seem to make a halo around the moon. But I think they look like the edge of a potato chip. They've got a period of between 7 and 14 days. They also come in different varieties. There's northern and southern. So northern spend time above the moon's orbital plane. The southern are below. There's the moon's orbital plane. And they're mirror images across the moon's orbital plane. They're characterized only by the AZ amplitude, since AX is coupled to AZ for these orbits. And this just shows the family. You could think of an entire family of halo orbits. On each energy surface, there's a halo orbit, for the case where they exist. So this is the L2 halo orbit family. Some are nearly vertical. This last one here. These are called near rectilinear halo orbits, or nearly rectilinear. They have shorter periods. So whereas it starts out for small AZ amplitudes, it's close to 14-day period, about half a sidereal month. The larger ones can have shorter periods. There's a question.
These near rectilinear halo orbits, they almost appear to be around lunar orbit. How close could that actually get to be, where you can distinguish that versus a very eccentric lunar orbit?
Yeah, they do appear eccentric, but they're frozen. They appear as frozen in the Earth-Moon rotating frame. So they are definitely orbits about both bodies. You need both bodies for this to happen. That's a good question. And this animation shows what that nearly rectilinear halo orbit looks like. In an inertial frame, try to make sense of that in terms of geocentric trajectory. And here's a moon-centered inertial frame, again, trying to make sense of it. In the Earth-Moon rotating frame, now we've got something. And this is, I think, under the full effects. So this is used by Capstone. Now, these orbits, because they do have some unstable component, they're unstable, so they need station keeping. And they they need to, in this case, maneuver would be needed at Apollo once per orbit.
What you plotted there is, if there were no perturbations, you've got pencil balance, and that's what we're seeing, right?
No, this was for capstone.
Oh, okay, so that is the progression over time.
Yeah.
You don't do station keeping, or you do?
Okay, I see what you mean. Yeah, this would be, they did station keeping, so this would have just been one thin line if we didn't include the MMRs perturbations. So there's also planar orbits. They're called Lyapunov orbits. Here's the family around L1 and the family around L2. They seem to be kidney bean shaped, so you have kidney bean orbits. I don't know if that's going to catch on. Muffler orbits. And these have the small amplitude orbits have periods of, again, about 14 days. And then the larger amplitude have a larger period. And these are in the moon's orbital plane. So if we want to look at the stability of these periodic orbits and some details about the trajectories that approach or depart, not the equilibrium point, but these periodic orbits, then we need to do some additional analysis. So I'm going to be talking for the next few minutes about stability of periodic orbits. This is the circular restricted three-body problem equations again. Right, it can be written as 6 first-order ODEs. Before we talk about periodic orbits, we can talk about just general trajectories. So if we have a reference solution, one shown schematically down here, starting at some initial condition x naught, or x bar naught, if we want to look at what nearby trajectories do, or understand what the linearized dynamics is about this reference trajectory, we conceptualize looking at small displacements or small perturbations. And if we had an initial condition with this initial small vector perturbation, what would happen to that nearby trajectory? How would that displacement vector grow? And that's given by what's called the variational equations. So this is this df is the Jacobian of the ODE. So this is a 6x6 matrix. Here is the 6x6 matrix. So you can think of this Jacobian matrix. It's a matrix that's a function of time and also the reference trajectory, and it has different components, including this, which is a bunch of second order or second derivatives of the effective potential energy function. So these solutions of the variational equations are known to be of this form. So x, the delta x at some time t is a matrix times delta x at the initial time. So this delta x at some time t equals this matrix phi of the initial delta x. So this state transition matrix encodes everything we want to know about the sensitivity of this reference trajectory. And we need to compute it along a reference orbit. We could rewrite the variational equation so that we actually get this down here. This is 36 ODEs for all of the components of the state transition matrix. So to get this state transition matrix, we compute 42 first order ODEs. First these equations of motion, and then these variational equations, with initial conditions being a point along our reference trajectory, and the initial state transition matrix is just the 6x6 identity. So you can do this. MATLAB can do this. MATLAB will do this in just a few minutes. Now, if we take a reference trajectory and then bend it back on itself, we've got a periodic trajectory. Right? So this is an example of a periodic trajectory. It forms a closed loop in the phase space. I'm just sort of showing a schematic here. Here's the blue, dark blue trajectory is the phase space, light blue are kind of nearby initial conditions, what they do. We could try to understand what's going on by taking a cross section or a Poincare section along the orbit and then looking at dynamics along that Poincare section. If we have a small displacement, then how does that displacement change? Well, we calculate what's called the monodromy matrix. This is the state transition matrix after one revolution along the nominal periodic orbit, period T. So after one period, so delta x after capital T, it equals this matrix M times the initial perturbation, whatever that initial perturbation is. We can look at the monodromy matrix for specific orbits to get the local dynamics. So this is just telling us M is the state transition matrix after one full period, one revolution. And this is another way of visualizing it, a Poincare section. And then if we were to look at a nearby initial condition and what it does, we could look at how it keeps piercing that surface. This is just showing a two-dimensional Poincare section. But of course, we have something that's higher dimension, but this gives you an idea. So if we want to look at what the dynamics are like along a periodic orbit, we look at the eigenvalues and eigenvectors of M. So now I'm going to focus on a halo orbit specifically. The criteria for stability and instability is different from the case for an equilibrium point. So this is a fixed point analysis of a map. What we're looking for are eigenvalues and how they compare in the complex plane, how they compare with the unit circle. Things that are inside the unit circle, those correspond to directions that are stable. If it's on the unit circle, it's sort of marginally stable. Outside the unit circle, those are unstable directions. So the first pair, I'll label them lambda 1 through lambda 6. Lambda 1 and lambda 2 are a pair, where lambda 1 is about 1,000, and lambda 2 is 1 over lambda 1, so it's much, much less than 1. And these are associated with the saddle-type character of halo orbits. So if you know about nonlinear dynamics, saddles meaning that there are directions coming in, there are directions going out. So if we were to take a cross-section of the periodic orbit, we have directions where things are leaving and directions where things are coming in. In fact, this lambda gives us an idea of how much things grow. So if you had something in the unstable direction, a small perturbation, that'll grow by a factor of 1,000 after one orbit. And same thing if you're along the stable direction, that'll shrink by a factor of 1,000. So the direction along which things are growing or expanding the most, that can be used to compute the unstable manifold. So these are trajectories that are leaving the periodic orbit. On the other hand, the eigenvector corresponds to lambda 2. That's the most contracting direction. So that can be used to compute the stable manifold. And that can be useful. If you compute this out backward in time, very far, all you have to do is get on the stable manifold, and the dynamics will naturally take you to the orbit you want to get to. So that's lambda 1 and lambda 2. Let me show schematically again the local stable and unstable manifold. So this green surface is the stable manifold, the stable directions. This orange surface are the unstable directions, and of course these both coexist. And if we were to kind of take a slice through it, it looks a bit like a saddle. There's unstable and stable directions. Here's another better image of that. So the stable manifold, these are, this is just showing it locally. If we globalize this, as in numerically integrate and take it much further from the halo orbit, really interesting things can happen. But it's all built on these small C's. So we've got stable directions and unstable directions. So we can continue kind of marching through what these eigenvalues are for a halo orbit. The second pair, lambda 3 and lambda 4, are both equal to 1. What's that all about? Well, the first eigenvalue, 1, is associated with variations just along the periodic orbit. So if you're on a periodic orbit and you perturb infinitesimally, either forward or backward, you're still on the same periodic orbit. You're just a little bit phase shifted. So it's kind of neutrally stable. The other eigenvalue is associated with an eigenvector pointing towards nearby periodic orbits. Remember I said these come in families, and this is pretty abstract here, but if you're looking at a periodic orbit on one energy surface, there's a whole continuum, so a whole family on nearby energy surfaces. So if you perturb in just those directions, you'll just be on a periodic orbit that's a slightly different period, but it's not going to grow exponentially or decrease exponentially. So those are the neutrally stable directions. The final pair, the third pair, lambda 5 and lambda 6, these are two complex conjugate values of modulus 1. So they are on the unit circle. And this corresponds to rotation. So this is related to the existence of quasi-halo orbits around the halo orbit. So near each halo orbit, there's a whole continuum of, think of them as tori, think of them as tubes. And trajectories, you could do formation flight, things all in the same quasi-halo orbit. In fact, there was some interest in doing this for the terrestrial planet finder mission about 15 years ago. And this is an animation from some of our work back then. So if we were to complete our picture of what all of the eigenvalues look like qualitatively for a halo orbit, we've got lambda 1 is much, much greater than 1 in real. So it's in the unstable. It means the halo orbit is unstable. Lambda 2 is inside the unit circle. It's a stable direction. We've got those two eigenvalues, 1, which are neutrally stable directions, and then lambda 5 and lambda 6 have something to do with this frequency of rotating around the quasi-halo orbit. So a halo orbit is called in the Hamiltonian literature a center-saddle type periodic orbit because it has saddle directions, and then this quasi-halo stuff are the center directions. We could look at what these stable and unstable manifolds do. We can just look at the stable manifold. By taking an initial condition and then integrating it backward. So this is showing an initial condition. Let me just show it. Here's our schematic of a periodic orbit and its stable and unstable directions. If we look at that in greater detail, x0, this is an initial condition on the halo orbit. And so we look in the direction of a stable eigenvalue multiplied by some small factors. And just the rule of thumb that seems to work is 10 to the negative 6 is okay, if these are normalized to unit. And I put plus or minus because you get two branches, right? Each of these stable directions is a branch. So it's be a positive branch, let's say, and a negative branch. So you start with that initial condition, and then you can integrate in the full equations of motion backward and generate a stable manifold. So this is a stable. This is a halo orbit, and we're showing it's stable. One branch of the stable in green and unstable in red, and it's just a continuum of trajectories. And that continuum of trajectories forms what we call a manifold. That just means a curved surface. Oh, there we go. Okay. So this is it for the Earth-Moon L2. This is the Sun-Earth L2. And we've got a halo orbit. And this just sort of shows growing one branch of the stable manifold, which we're calling a superhighway because it sounds cool. And then if you pick a halo orbit that intersected your chosen low Earth orbit, then in this case, once you got on that manifold, you would just sort of wind naturally onto the desired halo orbit. These things seem to form tubes. And if you actually look in the phase space, these tubes, if you're on the tube, that means you're going to wind onto or off of a halo orbit. If you're inside the tubes, though, it's inside the tubes that's related to the things I called transit orbits before. So these are sometimes called transition tubes. And this was known in the 1960s. Two mathematicians who had an interest in celestial mechanics, Conley and McGehee, found these locally and speculated on the use for low energy transfers to get to the moon. In the late 60s, there was a lot of interest in that. So if you have a particle that starts on this incoming tube, so this is a stable manifold of a periodic orbit around L2. If you're on that, then you'll just wind onto the periodic orbit. If you're in some sense inside the tube, so you're in some region of phase space bounded by that tube, then you'll actually pass by L2 and then get into this regime where you can be ballistically captured. If you're outside the tube, then what you'd see is something that just sort of comes in and then bounces back. So these are tubes in phase space, and they mediate this transport, which is one of their interesting properties. So this is another view just showing the transition tube and 3 of the phase space variables. And we often look at, on the Poincare section, that's where we pick initial conditions for, say, a transit and a non-transit. You can see what these do. Projected down onto the position space, the transit orbit seems to go right through this neck around L2, but the blue one is bouncing back. And so this is a way that we can design trajectories that say spend some temporary time around the moon and then maybe some temporary time around the Earth and so on. I might say some more about that, but now we're going to try this MATLAB exercise. And the goal here is just to gain some familiarity with these techniques, specifically just about periodic orbits, their stable and unstable manifolds, and so on. So we're going to simulate the circular restricted 3-body problem equations, and specifically for a halo orbit. So we're going to need to get an initial condition and period. We're going to start with a guess that comes from an analytical method. It's not the linear, it's not the first order method that I mentioned here. There's a third order method due to Richardson, and it's pretty good. But it gives you an initial guess that if you were to integrate it into full nonlinear equations, it might not fully come back. So it's not truly periodic. So you could use an iterative procedure, differential correction, to get something that's periodic within some desired tolerance. Maybe it comes back within centimeters. And then for that, we'll compute the monodromy matrix and the eigenvalues, and then compute the stable manifold using the stable direction. And this code, I know it works at least on my computer with MATLAB R2021B. I don't know how it will work with anything else. So if you haven't done it yet, and you've got your computer and it's not out of power yet, you can download this. It's the same thing I showed from before. And while you're doing that, I'm going to tell you a little bit about what the code does. So we're combining analytic approximations with numerical techniques to generate an accurate halo orbit. You can't just pick some random initial condition and hope that it's a halo orbit. I've had students do that in class. Terrible results. So this problem is well suited to a differential corrections process, which incorporates the analytical approximation as a first guess, and you iterate on that guess, basically using the state transition matrix. So this is aiming at producing initial conditions that lead to a halo orbit. So we use differential correction. We'll be using solutions of the variational equations along a reference trajectory, which in this case won't be periodic, because if it was periodic, it would be done. So we start with some initial condition that's a good guess. And then we calculate the state transition matrix. And from the state transition matrix, we can make adjustments to our initial condition. Because remember, the state transition matrix reflects sensitivity of the state at some later time to perturbations at some initial time. So if I wiggle, say, the initial x velocity, how will the final, will that affect the final state? The nice thing about halo orbits in the circular restricted 3-body problem is that they are symmetric about the xz plane. And that helps simplify things. So the xz plane would be coming through here. So trajectories have a mirror symmetry about the xz plane. And they intersect perpendicularly along that plane. So x dot and z dot are 0. There's only a y component to the velocity. Y velocity. So the initial state vector will be, we'll have an x naught, z naught, and then y velocity component. And we can get that from an analytic approximation. So there's a third order approximation that's actually built into the code. And then the nonlinear ODEs are integrated until we cross the XZ plane again. So basically we'll be starting at a point around here, integrating until we hit the XZ plane again. If this is a periodic solution, the final state vector would be, again, completely have only velocity in the y direction, but usually it won't. So the x and z velocities are not going to be zero, and we want to drive them to zero. So we drive them to zero using differential correction. In fact, we also, as a simplification, will set the initial z value so that it doesn't change. And then there's a submatrix, a 2x2 matrix that comes from this full 6x6 matrix that we use to find the changes, initial changes to x and the y velocity to get that perpendicular crossing within some tolerance. So the process is continued until the x and z velocity at the final crossing are zero. Not exactly, but within some acceptable tolerance. I forget what I put in there, maybe 10 to the negative 80. And usually there's convergence to a solution within 4 iterations. So with that, if you don't have the meta, I'm going to just sort of show you, and hopefully it works. Yeah, I'm just glad this works at all. So this is called a live script. So there's stuff down here. I'm not going to have any windows pop open because that annoys me. So this is what's going on here. This first part, and how do I make this larger? There we go. How do I get rid of this thing? Can I make that all go away? Yes, there it is. Okay. So all of this, you probably don't want to change. This mu, you could change if you want. I have it set for the Earth-Moon. If you wanted to get kind of wild, you could try the Sun-Earth-Moon. And just look at the Sun-Earth-Moon. It's like 10 to the negative 6. It's ridiculously small. Anyway. And then here you can set which Lagrange point you want. This is a non-dimensional z amplitude. Right? For halo orbits, it's just given by their z amplitude. And then this is, are we choosing a northern or a southern halo? And then it all goes into this third order guess. So we're getting an initial condition that comes from an analytical approximation that's third order correct. And if we just want to see what this initial condition does after one sidereal month, we can integrate it. So I've got this thing that integrates and then plots. So this is our initial condition. This is L1. And it does seem to hit the XZ plane, but then it does some other stuff. And I'm just showing the XY projection. So this is something that kind of goes around the moon, and then it leaves and kind of goes into geocentric space, right? The Earth realm. So we'll use differential correction. And if I were to run this in real time, you would see this change, but now I don't know how to recover that. Okay. Well, this shows that it had different attempts, and this actually converged in 5 iterates. This started out, right, not periodic, right? It has this crossing. We're looking for a crossing that's exactly perpendicular. And so we got one. So that means we have a good initial condition. Now we can actually get this thing called phi get, or phi underscore t. That's the monodromy matrix. And here are its eigenvalues. Notice one of them is on the order of 10 to the 3, and then everything else is pretty small. So we've got several that have unit modulus. Right, 2 of them are actually equal to 1, and then we have things that are kind of close to 1. This is the fully differentially corrected halo orbit. And am I able to grab this? I don't know.
One period.
Yeah, that's just one period. So that's the initial condition. And if I was able to rotate this, you can see it looks like the edge of a potato chip. If you add other perturbations, it's ruffles. But we don't have to talk about that. Ruffles have ridges. All right, so these are just other views of that halo orbit. And then we can compute a trajectory that's on the stable manifold and just integrate backwards. So that's what this is doing. We're integrating backwards. So if we started at this initial condition and went forward, we would get onto the halo orbit. But there's a whole continuum. So this is showing, I guess these are, I don't know what that is, some tick marks. They are not one day, so I don't know what's going on there. We could show several trajectories. So this is showing several trajectories along the stable manifold. So this would be, if you wanted to leave the moon and get onto this particular halo orbit, you would maybe look for the one that comes closest to your lunar orbit. And I think that's it. Everything else are functions. So there's 1,000 lines to this code, but most of it is functions. And you are welcome to kind of mess with this stuff if you want to. I'm not going to mess with it anymore. I'm lucky it did anything. So if you get it to work, great. And you're welcome to share with others. This code isn't proprietary or anything. I don't know. Figure out some way to cite me. I have a book I'll mention at the end, and you could cite the book. That would be great. All right. So that's the MATLAB demo. So I've been saying a lot of stuff about the Earth-Moon system. But the Earth-Moon system, cislunar space generally, is dynamically connected to heliocentric space. And here's one way. You could look at halo orbits in the Sun-Earth system, like Sun-Earth L1 and L2. Here's the Sun-Earth L2, and here's a stable manifold of it. This is an artist schematic, but it's not too far off. And this is connected to an unstable manifold coming from the moon. So you could go from the region around the moon to basically the edge of the Earth's sphere of influence. So this is just artist rendering to give you an idea. It's not a real calculation. But we're showing the Sun-Earth L2, and here's Sun-Earth L2 halo orbit. And then there's the Earth, there's the moon, and then we've got the Earth L1 and Earth L2 and some halo orbits around there. And this has stable and unstable manifolds. So if we wanted to go from an orbit, the Lunar L1, represented by that ball there, we could release it, and if we gave it just the right nudge so it's on this unstable manifold, it'll go through that unstable manifold, kind of go into the tube related to this stable manifold of L2, and now it's sort of inside the tube, not really on the tube. And this thing will, without any delta V's or anything, intersect and then get onto the Earth L2. And if you had something there that you wanted to deploy or repair, I don't know, like a space telescope, you can reverse this process and maybe bring it back to cislunar space for repair. But I won't show you all of that. Let me show, this is an actual trajectory. So I'm showing here a lunar rotating frame, something leaving an L1 orbit, a small delta V, passing by L2. This is what it looks like in the solar rotating frame. So this is the Sun-Earth line. There's the moon, and then that's our trajectory. And after that delta V, there's no maneuvers here. And this is a solution of the four-body problem. So this is going on to a rather large, but it is still an L2 halo orbit. And this is an object that Aaron alluded to earlier, I think. This is a Saturn V upper stage from Apollo 12 that kind of returned after 30 years absence, did a little dance, and then left. So it came in, it must be in the Case 1 regime in the Sun-Earth system. So it came in, moved around. I don't think it had a close encounter with the moon. It's just sort of doing something, which we would expect being in the Earth realm and viewing things with the Sun-Earth rotating frame. And then it left. And it's going to be on a heliocentric orbit and maybe come back around 2040. Because this encounter was in about 2002. All right.
So, but when you're kind of designing those trajectories, if you want to go from halo orbit around the moon one of those to the heliocentric,
Yeah.
are you just patching together the circular three-body equations
To get an initial
and
condition.
finding
Yeah.
conditions where the A condition here meets the initial condition there?
Yeah. And then when we put that in a more realistic model, it seems to do pretty well. Like you can use differential correction again there to get something more. Yeah. So the last section, I'm going to say some things about mean motion resonance. I like seeing movies, and this is a cheesy movie that I found online. A hypothetical Jupiter and Saturn in a 2-1 resonance. So they seem to match up after Jupiter does 2 periods for every 1 period of Saturn. So these resonances can be important. And we're talking about resonances between the spacecraft's orbit around the Earth and the Moon's orbit around the Earth. So in an inertial frame, here's just an example over 1 lunar orbit. This is the outer gray dot is the motion of the Moon, and then the spacecraft is the black dot. This is a 2-1 resonance. Right after the Moon goes around just half, the spacecraft has gone around once, and after the Moon's gone around once, the spacecraft's gone around twice. So this is called a 2-1 interior resonance. If you look at it in a rotating frame, this is sort of a stylized idea of what it looks like. At time 0, we have this, and then so we've got a periodic orbit in the rotating frame as well. This is a stable resonance because this has a close approach to the, when it's along this syzygy line, the x-axis in the rotating frame, it's at its furthest point from the Moon, right? It's at apogee. This is an example of an unstable mean motion resonance. So here now the phases are slightly different. If you look at things in the rotating frame, it's still a 2-to-1 resonance, but it's an unstable one, meaning slight perturbations, and this is going to be this orbit. So this is a very fragile orbit. If we were to use the same sort of calculation and hit the monodromy matrix, we'd find this periodic orbit in the rotating frame is unstable, and this one is stable. So you can have mean motion resonances that are stable and unstable. And just for fun, here's a 5-1 resonance, a red trajectory that's in both the inertial and rotating frame. So the 5 petals can reveal that's a thing. So if we view, if we want to do something where we can see not just individual mean motion resonances, but all the dynamics all at once, there's the technique from nonlinear dynamics. We have referred to it before, the Poincare section, but now we're looking at just a whole bunch of trajectories. You look at it, we start with a grid of initial conditions, typically at the same 3-body energy, and follow where they go. So we could look in both the exterior realm or the interior, so this means realm around the Earth, realm exterior. And this is what the Poincare section gives you. You've got initial points, they kind of come back as things go around in the rotating frame. And you'll always see something like this, where there's sort of this scatter shot region, and then these look like target patterns. This is in the Earth-Moon system. It looks kind of like an angry face. And we're overlaying some periodic orbits and things. But this is what is called a mixed phase space structure. So we have stable resonances, these closed curves, sort of going in on the target pattern. The middle of the target pattern would be an exactly periodic orbit. And the closed curves are quasi-periodic orbits around it. And then that sort of dissolves into what is poetically called a chaotic scheme. Right? This is looking at things in the Cartesian coordinates of the rotating frame. And it is kind of scary. Kind of literally scary. So we usually transform to geocentric orbital elements for easier interpretation. So this would be a Poincare section, but now we're looking at, this is the non-dimensionalized semi-major axis versus the angle of periapse. And this is in radians. So if this is a resonance. In fact, this is the 2-3 exterior resonance. So that dot there corresponds to a periodic orbit that's stable. Not shown, there's an unstable periodic orbit, but this region around here, we can call this the resonance region. So it's the 2-3 exterior resonance in this example. And if you start not in a resonance, if you're in a resonance, you'll just sort of see that you see. But if you start in an initial region that's in the chaotic sea, so here's an initial condition that corresponds to a relatively small semi-major axis. And as it evolves in time, so this is every time it pierces this surface we define, I'm putting a dot. So sometimes these jumps are big, and it seems like we're going around resonances. So we do move around resonances, and this leads to large changes in the geocentric orbital elements. So we can calculate these things. So these things that were shown by the fast Lyapunov indicator maps in Aaron's talk, we can actually calculate these things, the geometric structures behind it. And it's stable and unstable manifolds of unstable periodic orbits. In this case, we've got that same 2-3 resonance. There's the stable one right in the middle here. Who cares about stable stuff? We're looking for the unstable one. So there's an unstable periodic orbit here, and we're showing the unstable manifold in red and stable manifold in green. And we followed it very far. And so you could look at multiple resonance regions and how they intersect, so that criteria that the overlap of resonance is what leads to chaos. Well, this is the sort of geometric engine behind it, and you can navigate between these resonance regions. I've done some work looking at a semi-analytical model for looking at multiple lunar flybys, where we look at the Hamiltonian, the rotating frame, but we use Delaunay variables. And so the evolution is Hamilton's equations, and we're particularly interested in this evolution of the angular momentum, because we use something called Picard's approximation to find out what is delta G, what is the effect of the moon's perturbation over one geocentric orbit. So we can consider that. And then we can turn that into what's the change in the Keplerian energy over one orbit. And we get a curve that looks like this. This is the kick function. And you'll notice that it's odd in the argument of periapse. And you have zero kick right at argument of 0. This means this is 0 in the rotating frame. But a little bit before, a little bit after, you have large changes. And I think this is a nice way to look at it. If this is the Earth, this is the Moon. If you have something coming in, and in the rotating frame, it has its close approach right in front of the Moon, that gives you the largest drop in your semi-major axis. If it's right behind the Moon, at this minimum here, you get the largest kick in the semi-major axis. So just by slightly changing, if we started over here, this negative x-axis, and did some slight change, we could choose whether we want to get the maximum kick up or down in the semi-major axis. If you do this repeatedly, you can get very large changes. So we can construct an update map. And I'm looking just in the exterior here. The same thing could be done in the interior region. So interior. We haven't said anything about resonances yet. This is just a map. So we take the average perturbation per orbit, and we can go from one set of orbital elements to another. The cumulative effect of consecutive gravity assists can be really dramatic. The interesting thing, though, is this is occurring outside the sphere of influence, or at least any definition that you can think of for the sphere of influence that's been given. This is outside of it, and yet you get these changes. And this is all in the same Tisserand parameter. And so think of, you know how that showed how A and E change? Well, every time we have a flyby, the Tisserand parameter stays basically the same, but we're jumping in semi-major axis. So this is the update map in the argument of periapse with respect to the rotating frame and the Keplerian energy. And we can use a lot of machinery from Hamiltonian dynamics if we want. This map is also a Poincare return map at periapse in the orbital element space. If we started with some initial conditions in the chaotic sea, and then just follow them forward, we get this, and you can see it's sort of going around these, it looks like Swiss cheese, we're going around the holes that correspond to stable resonances. If we do the same thing with the full nonlinear ODEs, we get something very qualitatively similar. So this Keplerian map is sort of a fast orbit propagator. And this shows an initial condition that was carefully chosen, that this triangle up here, that after so many iterates, it goes around, so that means so much time. It goes from one semi-major axis to another. And then these are naturally connected to ballistic capture. So if you think of, we're doing a Poincare section, once you get to this little sliver here, this is where that tube of orbits that's going to be captured by the moon intersects this Poincare section. Then you go into the moon region. So it's kind of an exit from the geocentric on the way to the selenocentric region. And this is, you have orbits that reach the exit that are ballistically captured. So let me show this example again, because this is a trajectory that, after an initial large delta V to leave that geo radius, there were just two other delta V's used. One was used, I think around here, where we had a close approach to L1, and then a final one just to get onto a stable orbit. And those added up to less than 100 meters per second, after having left geo. So this used the connection between resonances and these ballistic captures. Hopefully this gives you an idea of the type of phenomena that are possible. This shows that I'm showing the fuel time trade-off that's common with delta V versus time of flight. This is in days. To go from a particular geocentric orbit to a particular selenocentric orbit. If you did the Hohmann transfer, that takes the lowest time of flight, but it takes large delta V. Some other authors have looked at things that take 2 years and use less delta V. But it looks like there's some kind of Pareto optimal front here, and so some work that we've done sort of fills out some of that front. The question that sometimes comes up is, do these phenomena persist when we add more realistic models? So for example, including the effect of the sun, that's something called the bicircular model, or including the effect of the moon's ellipticity, the elliptic restricted three-body problem. And when we do go from the simplest models to more realistic, the main phenomena remain largely unchanged. So this is sort of a hierarchy of models going from the circular restricted three-body problem up to the real ephemeris. And this is some work by Kathy Howell's group. So this is that near rectilinear halo orbit that I showed before in the circular problem, circular model. We kind of go up the ladder in the bicircular model. So this includes the solar perturbation. See, it doesn't exactly come back onto itself, but it's close. And in the real ephemeris, okay, there's a bit more going on, but qualitatively, I would say it's very similar. And the same thing is the case for the phenomena I talked about with stable and unstable manifolds and transit orbits. Instead of having an equilibrium point in the circular problem, when we go to the elliptic or the bicircular problem, there's a dynamical replacement of L1 and L2, which is a periodic orbit. And if you go to more accurate models, the periodic orbit will bifurcate to quasi-periodic, and so on. So we've got some work. This is current PhD student about to graduate, Josh Fitzgerald, who published there. So I'm done. Let me give you some main references. I really like the Solar System Dynamics book by Larry Dermott. Maybe I've got the wrong year. But it's very good. And then I've got a book that's free. You can download. I think I also put it in the folder for this course. I've also got a whole course on Hamiltonian systems, nonlinear dynamics and chaos, and I'm starting on the three-body problem. And you can find those on my YouTube. So with that, thanks.
If you appreciated this video, please like and subscribe.